So we are covering the second part of Chapter 2. We are going to review how we use our best friend the periodic table, looking into ionic versus covalent bonding, and nomenclature. So nomenclature is going to be a huge part that carries throughout the course. So we want to make sure we have our nomenclature down, which means we also need to remember those polyatomic ions. And the last section is more applied to lab, but thinking about mixtures and how we can separate them based on their different properties. So here's the periodic table, and remember that you will always have a periodic table. So we want to make sure we know how to utilize it and all the information we can gather from it. The first thing being, we can look at the group numbers to figure out a charge. So remember that we want to, the whole reason for undergoing bonding or undergoing gaining and losing electrons is to become stable. So based on that, the periodic table we can use to figure that information out. If I am a metal, I'm going to be more likely to lose electrons to gain stability, which means I'll have a positive charge. So we have all of our metals located on the left side of the periodic table. We have our metalloids along this line, and all that means is that they have some metal-like properties and non-metal-like properties. To the right of that line, we have all of our nonmetals. So our nonmetals, instead of losing electrons, they like to gain electrons to become stable. So as ions, they like to have negative charges. So looking at the periodic table, if we think about losing electrons for metals to gain stability, all the elements in group 1A are going to want to lose one electron to become stable. So for example, if I take sodium, I lose one electron. I now have the same number of electrons as neon, and we know that our noble gases are very stable. So all of those in group 1A and also hydrogen, they're going to lose one electron to have a +1 charge. Group 2A, so the alkaline earth metals, these are going to lose 2 electrons to become stable. For example, if I'm magnesium, if I lose 1, 2 electrons, I have the same number of electrons as neon, I am going to be stable. The transition metals are going to be a little bit different. So we call these elements that are going to be in our first 2 groups, and then on the rightmost side of the periodic table, this whole block, those are going to be main group elements. We call them main group elements because they have very predictable charges that they form. Right in the middle, we have our transition elements, our transition metals. Those can have different charges. But the thing to keep in mind is that they will always be paired with something that we know the charge of, so we can figure out the charge. So these are variable. If we skip over to group 3A where boron is, these like to have a +3 charge. So for example, if boron loses 3 electrons, it now has the same number of electrons as helium. We're not going to worry as much about group 4A because they can actually do different things. They can gain electrons to become stable, lose electrons to become stable. So carbon, for example, can have different charges depending on what it's paired with. So if we move on to nitrogen, now we are in nonmetal territory. These are going to want to gain electrons to become stable. So if I am nitrogen and I'm gaining electrons, I'm going to gain 1, 2, 3 electrons to be like a noble gas, which gives me a -3 charge. For oxygen and its elements in that same group, I want to gain 1, 2 electrons to become stable, so I will have a -2 charge. And for the halogens, so fluorine, chlorine, bromine, iodine, those are going to want to gain 1 electron to become stable, giving them a -1 charge. Noble gases are already perfectly happy the way they are. They don't want to gain or lose electrons. So these are the things we want to be able to gather from the periodic table. There are 4 exceptions that I want you to know. Okay, we said that for the transition elements, those can have variable charges. The 2 that we want to know that will actually always have the same charge, just like a main group element, will be silver, always has a +1. Zinc always has a +2. Okay. From our main group elements, we also have 2 exceptions that I want you to know. For tin, even though it should have its main group element should have the same charge all the time, it can have variable charges, usually a +2 or +4. So that is an exception. Our other exception of the main group elements is going to be lead. It can also have a variable charge, also +2 or +4. So ionic compounds, we said we have two ways to become stable. Either we can gain or lose electrons, which is what we're going to do to form ionic compounds, or when we get to molecular elements, that's when we're forming bonds to become stable. We're sharing electrons. In this case, if we think about sodium, we know it's a metal, wants to lose electrons to become stable. Chlorine is a non-metal, it wants to gain electrons to become stable. So when we bring those together, this is what happens. Sodium gives up that electron, gives it to chlorine, and now in its outermost shell, both of them have what we call an octet of electrons. So that outer shell is filled. It has the same electron configuration as a noble gas. So sodium gets a plus charge, and chlorine becomes chloride and gets a minus charge. But again, the whole idea is I want to be like a noble gas. I want to be stable. And this is one way to do it, to gain and to lose electrons. Both gain stability. Okay. If we want to think about strength of ionic bonding, and again, ionic bonding is going to be when I bring a non-metal together with a metal, so I'm losing and gaining electrons to become stable, right? So Coulomb's law says that if I have, for example, an ionic compound, and I have something with a +1 and -1 charge, and if I compare that to something that has a +2 and a -2 charge, the strength of the ionic bond is going to be greater if I have a higher charge. Okay, so the one with the +2 and -2, that will have a greater ionic bond strength. Now if I compare where I have the same charge, so both of these are +1, -1, +1, -1, but now I have this one that's a lot larger. So both of those ions are a lot larger than the ones on the right. I want you to take a moment to think about what you expect. You can pause the video if you like. Okay, so the ionic bonding is going to be stronger for those ions that are smaller, and that's just because they can get in closer together. So our next big topic again is going to be nomenclature. And nomenclature is, I can't stress enough, it's going to become so important. So let's say down the line we're working on a problem and I give you the name and I don't give you a structure. You can't even tackle the rest of the problem if you don't have the structure that you can gather from the name. Okay? But in our everyday lives, nomenclature is on a lot of the things that we see. So if I look on the back of some medication I'm using, I'm going to see all these different terms. And if we know something about nomenclature, maybe even if we don't know those specific terms, we can start to piece together to get an idea of what it looks like structurally. So I think it's pretty interesting. Common everyday things like baking soda. We have sodium bicarbonate. That's its chemical name. If we look at things like calcium carbonate, that's going to be chalk. If we look at the different ionic compounds that allow us to have those cool glow-in-the-dark stars, at least I had them growing up, those are going to also be ionic compounds. So it's really interesting. If we know basic nomenclature, it allows us to name a lot of the things around us. So this is a table that I would take some time to really look through and get some practice with. So we have all of our nomenclature summarized in this table, and it starts with looking at ionic versus molecular compounds. Okay, so I want to walk you through this table because it's pretty important. Okay, so let's walk through the table. The first thing we're going to do is, if we have an ionic compound, we have to identify it as an ionic compound if we're going from the structure to the name. So we need to have a metal and a non-metal. Now we know we're in ionic territory. And we have two types. We have type 1 and type 2. And the only difference between the two is going to be the type of metal we have. So we talked about the difference between main group metals, and those are going to be type 1 because they have the same charge all the time. We don't need to tell anyone what the charge is because it doesn't change. Whereas type 2, these are mostly going to be our transition metals. These ones can have several different charges. So in the name, we have to add something to it to specify what charge we're talking about. Are we talking about copper with a +1 charge, for example, versus copper with a +2 charge? And we use a Roman numeral to tell the person we're communicating that information to which one we're talking about. All right, so let's start with type 1. So I have a main group element. I have something like calcium or sodium that always has the same charge. The first part of the name is going to be just the name of the metal itself. You'll be able to get it straight from your periodic table because you'll always have it. You'll have a space, and then you are going to put the base name of the anion. It may be helpful actually to pause the video and take out your handout on nomenclature, and you have all of the base names summarized. At your handout, you have the base names on the second page. So for example, for a fluoride group, it's going to be fluor, chlor for chlorine, brome, iode, and there are a few more. If you have an oxygen, it will be ox. For sulfur, sulf, and for nitrogen, nitr. So these base names we need to know. And what you'll do is you'll drop the ending and you're going to add IDE to the end. So fluoride, chloride, bromide, iodide. So we have that for the type 1 ionic compounds. So type 2 is actually going to be very similar. So you're going to name the cation, which is going to be the metal. Our only exception is if we have an ammonium ion, which is going to be our one polyatomic ion that is our cation. And the thing we need to add here is going to be what charge we are using. So for example, if I determine that it's copper with a +1 charge, in Roman numerals, I need to put a 1. So that way the person knows I'm talking about specifically copper 1 and not copper 2 or some other copper. But the base name is exactly the same. I'm going to put the base. So if it were, for example, copper chloride, the +1 charge, I would have copper in Roman numerals 1, and then chloride. Okay, so what I would do is just make sure you're making note of your questions you have. All right, so that's type 1 and type 2 for ionic compounds. Now we move on to molecular compounds, and the first thing we need to identify is for sure that it is a molecular compound. If I have 2 or more nonmetals that I'm bringing together, now you need to move on to this nomenclature. So with a molecular compound, we start with a prefix. So if I have something like N2O, right? This is where I have to learn the prefixes that are also listed on your handout. We only use these for molecular compounds, but mono, di, tri, tetra, penta, all the way up to 10, those are ones that we need to know. Okay, so if I, for example, again have N2O, you can go ahead and write it down if you like. Since the N has a subscript 2, I have to put di in front of it. And then the name of the first element. So it'd be dinitrogen. And then for the second element, if it's N2O, I only have 1 oxygen. So it would be mono, and it would be nitrogen monoxide. So base name of the second element, just like we did for the ionic compounds, we're going to drop the ending and add IDE. So if it's oxygen, it would be ox for the base name, and then ide is what we add at the end. Notice that it's not monoxide. Okay, if you have 2 vowels next to each other, you drop 1, so it becomes monoxide. Okay, so it'd be dinitrogen monoxide. One thing that we want to make note of for molecular elements in their names is if I only have 1 of the first element, I don't have to put mono. Okay, so mono is only used for the second. Another example of this is CO, and if you want to write that down, you can. I don't say monocarbon because I don't use the prefix mono for the first element. So it'd be just carbon, and since I only have 1 oxygen, it would be carbon monoxide. Carbon monoxide. Now we're moving on to naming acids, and the first thing you may ask is what makes something an acid? And that is when you're going to have hydrogen out front as the first element. So this H plus that we'll talk about in more detail, when we put it into solution, when we drop it into water, and it breaks apart into ions. This H plus is what makes it an acid. So that's what we're looking for. We have essentially two types of acids. Binary just meaning that it doesn't have any oxygen in the formula, and then oxyacids are going to contain oxygen. So let's start with binary, something like HCl or HBr that has no oxygen in it. We always use hydro out front. So hydro, if we're talking about HCl, for example, we have hydro. The base name of chlorine is going to be chlor. And to that we add ic at the end. So it would be hydrochloric. And then we have a space and we tack acid at the end. So hydrochloric acid. Same for HBr, hydrobromic acid. For HI, hydroiodic acid. If we move on to oxy acids, these are going to be ones that contain oxygen. So most of the acids we're going to look at will be oxy acids. And here's where polyatomic ions come into play. So hopefully you've started looking at your polyatomic ions, and we'll review them in just a moment. But what we have to do is pay attention to the ending of the polyatomic ion. So that will make the difference in the way we name it. So one example is sulfuric acid versus sulfurous acid. They are very different. So the first thing we need to do is look at the formula and identify that polyatomic ion. So if I'm looking at the formula, and I would write this down, and it says H2SO4. Okay. If I look at the SO4, I know that that polyatomic ion is sulfate, right? I know how it has a -2 charge, so it needs 2 of these +1 from the H pluses to pair up with it to make sure that it's neutral. Okay. Once I've identified that SO4 is sulfate, I'm going down this path. So since my polyatomic ends with 8, this is the way I name it. So I want the base name of the oxyanion, which is going to be sulfur, okay? And then I'm going to add ic to the end. So if my polyatomic ion ends with 8, I will have ic at the end. It will be sulfuric space acid. Okay. Now, if I look at H2SO3, we know that SO3 2- is going to be sulfite instead. So now I'm going down this pathway, and instead of having ic at the end, I have us. So it will be sulfurous space acid. Okay, so we also need to know our polyatomic ions to be able to name acids correctly. So I have here just a list of some common monatomic ions, and most of these you can get straight from the periodic table. Again, we want to make note of our 4 exceptions, so silver and zinc, and then also lead and tin are going to be our exceptions. We have just a reminder of where we find all of our +1, +2 charges, -3, -2, -1 for our halogens. Notice that hydrogen can be +1 or -1. If it is -1, we call it hydride, so that's something else to add. And then you can look at our 4 exceptions: silver, zinc, tin, and lead. Here are just some other monatomic ions that these are all going to be the transition metals. So notice that they have different charges, and we have our systematic names. So these are the ones that I want you to know, where we're adding the Roman numeral to tell what charge we're talking about. The common names I put here, I will not test you on them, but you may run into a case where you do see some of these terms, so I want you to at least become familiar with them. So instead of saying copper 1, we could say cuprous. Instead of saying copper 2, we can say cupric. They mean the exact same thing. For our polyatomic ions, so we are going to play some games and hopefully get these down, but these are things that we need in our toolbox. There's also a Quizlet app posted on Canvas that you can pull up your phone, and if you have 5 minutes here, 5 minutes there, you can test yourself. But again, in order for us to do other problems, we have to have the naming down, and in order for us to name, we have to know our polyatomic ions. Acetate, I want to point out that you'll see it written this way, or you'll see it written as C2H3O2 minus. They mean the exact same thing. This is just showing more of how the atoms are connected in the structure. So the ones that are on your handout are the ones that I want you, that I expect you to know. All right. Looking at some of the polyatomic ions, especially for example the chlorate, we have a lot of them. So how do we keep these straight? And what I would do is learn the one that has no prefix first. So if I just have chlorate and the one that has ATE at the end, and then we can figure out the ones above and below it based on the number of oxygens. So here's one example. So this works for oxyanions. For chlorate, I have 3 oxygens, and when I think of per, I think of hyper or more. So for perchlorate, I have always 1 more oxygen, so I have ClO4 instead, and then I is always going to be 1 less oxygen, and then hypo means less, so I'll have 1 less oxygen than the ite, and that's the way I always organize it. So learn the one without the prefix and the one that has 8 at the end first, and then you can figure out the other ones from there. Okay? I always like to memorize less if I possibly can. So let's look at what's wrong with each of the following. Okay? In A, we have Ba. So again, this is the other way that we write acetate. Okay, so this is another way you'll see it. And it says that it is called barium diacetate. So you may want to pause the video, take a moment. What's wrong with this? So something we want to keep in mind is that we only use di, tri, tetra, etc., those prefixes, if it is a molecular compound. Barium is a metal. This is definitely an ionic compound, so it would just be called barium acetate. No di needed. Right? For this one, we have sodium sulfide, and this is the formula for it. What's wrong with it? Okay. Something we didn't point out before is that we're only using the parentheses if it is around a polyatomic ion, and we have to have more than one of those, that particular polyatomic ion. So sodium on its own does not need any parentheses. Okay, the charge balance is correct, but no parentheses needed. For iron 2 sulfate, let's look at the formula. So we have Fe2 SO4 3. Go ahead and take a minute. What's wrong with this formula? So if we think about it, if iron has a +2 charge, we know from the Roman numeral, sulfate, our polyatomic, has a -2 charge, that already has charge balance. So the correct formula should just be FeSO4, nothing else needed. Let's look at the next one. For cesium carbonate, we have this formula. So CS2CO3. Go ahead and take a minute. So the charge balance is correct. If we have cesium with a +1 charge, we do need 2 of those to balance out the carbonate. But the problem is we have just 1 CO3, 1 carbonate, so we don't need the parentheses. We only need them if we have more than one of that polyatomic ion. Okay. If we now look at covalent bonding, this is going to be where we are now sharing electrons. So we have 1 electron coming from this hydrogen, 1 electron coming from the other hydrogen, and we're sharing. And it's one of our exceptions to the octet rule. Hydrogens only need 2 electrons to be happy. So now it is stable. Okay. Again, if we are going to name covalent compounds, so covalent, molecular, they are the same thing. Now we need those prefixes. So these are the ones we need to know. I want you to know up to 10 to deca. And a little bit of organic chemistry. So I am an organic chemist, so this is near and dear to my heart. But I want you to know just some of the basics. This is going to be an alkane. Alkanes are going to have only carbons and hydrogens in their formulas and only single bonds. So that's what gives it this ane at the end. If we have a ball stick model, this is what it looks like. Okay, so organic chemists, we draw what we call line angle structures, or these zigzag lines, and that's because it allows our atoms to be spaced out as much as possible. Okay, so again, contains only carbon and hydrogen. Ane means it only has single bonds. What we want to know are the root names. So from 1 carbon to 10, I want you to know the name of the alkane. So we also need to know these prefixes, which are a little bit different from the ones we learn for just molecular compounds in general. So meth means 1 carbon. All of them are going to have the ending ane because they have all single bonds. So methane, ethane, propane, butane, and so on. Okay, so again, the prefix tells us how many carbons are in the long linear chain. Thinking back to other tools that we need in our toolbox, in the next chapter we are going to start doing some calculations and figuring out different properties about compounds and chemical formulas. Something we want to make sure we know how to do is how to calculate a molecular mass from a chemical formula. So the nice thing is, again, we can use our best friend, the periodic table. We can take the individual masses of each atom in the molecule and just add those atomic masses up. So for example, with water, I have 2 hydrogen atoms, and here is the mass straight from the periodic table in atomic mass units. I have 1 oxygen, and I can take that mass straight from the periodic table, multiply each one of those, and then add them together, and this gives me the molecular mass of the compound as a whole. Okay, just some more terminology. If we are talking about just an element itself, we say atomic mass. If we're talking about a molecular compound or covalent compound, we say molecular mass. And then if we are talking about an ionic compound, we say formula mass, but they all mean the same thing and you go through the same process. We have a few different ways that we can represent molecules, and I wanted to just show these to you because we'll be seeing them throughout the text. We have a molecular formula, so something else to keep in mind is when I'm asking you questions, you want to know what I'm referring to. Structural formulas, ball stick models, and then space filling basically shows the electron density that particular molecule takes up. So our last topic is going to be separating mixtures, which I did a lot of in grad school as an organic chemist. So it's a topic that really interests me. And the first thing we need to do again is to classify a mixture as either being homogeneous or heterogeneous. And based on that, we have different tools that we can use to separate out the compounds in the mixture. So as a reminder, a homogeneous compound is going to be one where I have 2 or more substances, but the ratio of those 2 or more substances is going to be equal throughout. So if I take a sample, for example, from the top and from the bottom, the ratio of those substances should be exactly the same. Whereas for heterogeneous, the ratio of those substances is not going to be the same throughout. So we took the example of pizza or trail mix being heterogeneous mixtures. And the way we separate them will be different. Okay? I want you to stop and take a minute to think about why we spend time talking about separating mixtures. Why do you think this is a huge field, and why is it so important in industry? So here are a few. There are many different separation techniques, but these are just going to be a few of them. So filtration is going to separate compounds out based on particle size. One is, for example, if I have some liquid and sand, I can always do a filtration. Crystallization is going to take advantage of differences in solubility, and this has to be used for something that is a crystalline compound. Distillation is great for liquids, and it separates compounds out based on their boiling point. Extraction is where you can separate compounds based on their difference in solubility in different solvents. And chromatography can apply in a lot of different ways, but it can separate compounds. These can be liquids, they can be solids, but it separates them based on mostly polarity and also on size. So a simple filtration, again, we talked about the example of having something like salt and some liquid. And because in that case we have a huge particle size that will get caught by the filtration paper, we can just put them both through, and the solid will sit on top, the liquid will flow to the bottom, and we can always rinse with more of the solvent to get all of our compound out. So filtration is a nice one if you can do it. For a distillation, this is the setup. So again, it's going to be for 2 or more liquids, and you put both of your mixture in here, and you have what's called a heating mantle. And then we have, if you go up, this is a condenser. So the idea is you're going to be heating it up, and the one that has the lower boiling point will go into the gaseous phase first, and then you cool it back down using the condenser to go back into the liquid phase, and then you can collect it on this side. And then you can always replace this with another flask, heat it up a little higher, and then your compound that has the higher boiling point will now go into the gaseous phase, and then you'll cool it down and it will go back into the liquid phase for you to collect. So it's very useful, especially with organic compounds. Decantation. If you can do a decantation, this is a nice one too. So for going back to our liquid with sand example, filtration is one way to do it, but sand is going to sit at the bottom of something so nicely that you can usually just pour the liquid off the top. So that is a decantation. For chromatography, again, it will separate compounds out based on mostly polarity, but the way it works is you have a stationary phase, which will be what we call silica. It's basically a substance that is very, very polar. And then the mobile phase will be solvent that you run through the column. So you put the solvent through the top and it runs out. And compounds that are really, really polar, they tend to interact with the silica really well, or we say it sticks to the silica. So they take longer to move through the column because they're interacting with the silica. And then compounds that are more nonpolar or more grease-like, they will interact a lot less with the silica and more with the solvent, so they pass through a lot faster. Okay, so nonpolar compounds will come out of the column first, and then more polar compounds that stick to the silica will come out last, and you can collect different fractions. So here we have it shown being collected in flasks, but you could also do this in test tubes, and then you can see separation. Right. The same concept can be applied to smaller amounts of compound. So if you run a column, you're trying to separate out larger amounts of compound. But in something like gas chromatography, you may just want to test to see if your sample is still a mixture, is it pure? So basically testing the purity, but the concept is the same. So you have a stationary phase, that's silica, and then you have, instead of a liquid phase or solvent, you have gas running through it. So that's what's called your mobile phase. But the same idea, if I have more polar compounds, they interact with the silica more and take longer to come off. And then if I have something that's more nonpolar, it doesn't interact with the silica so much, it comes out pretty quickly. So you run your sample through, and for gas chromatography, usually you have something called a flame ionizer detector. So at the end, it basically burns your sample to create a signal, and then the detector picks it up, you get this signal, and then you get these different peaks for your different compounds that come out, and you can look at the area under the curve to get a ratio of the compounds you have in your mixture. So it's a really good tool to check purity. The last one is going to be an extraction. So you probably won't do this in general chemistry, but for those of you moving on to organic, it's a partition between two phases. So you usually have an organic phase, or what we think of as an oil phase, usually on top, but it depends on what solvent you're using. And then you have an aqueous phase or a water phase. And based on differences in reactivity, you may have some compounds that move into the aqueous phase. So let's look at one example. We don't know what this structure means exactly because we haven't learned line angle structures, but all of these vertices represent carbon. Organic chemists are a little lazy in that way. We don't like to draw on our carbons or hydrogens, but this is a compound that only has carbon and hydrogen in it. So it is a hydrocarbon. And then we have something called benzoic acid. It is acidic. So what I can do is I can take advantage of the difference in reactivity. Now initially both of these will be soluble in the organic phase or the oil phase on top, but if I react this acid with base, now I generate something that is charged. We call this a carboxylate. And then the naphthalene that doesn't react at all, it will stay in the organic phase because it's still soluble. But once I make something that has charges and ions, now this is going to be soluble in the aqueous phase. So I've now separated them out. They both started in the top phase, but once I added in the base to react with the acid, this carboxylate that I generated moved into the aqueous phase. And then you have a little stopcock that you can open up to separate the two phases. So it's a really nice tool that's commonly used in our organic laboratory.